Alright, what's up guys? I'm going to go over some Minecraft Redstone and some cool things you can do and the connection between Boolean algebra and propositional logic and truth tables. And Redstone, of course. So this is my little super flat world for Redstone. I'm just going to go over some of the things you can do with Redstone that allows you to express logical statements in Minecraft. So firstly, we have an inverter, or the NOT gate, and that's simply just redstone. And a redstone torch changes or inverts the signal. Here's my AND gate. You have two signals. If both of them are on, then both torches are off, meaning there's no signal, meaning this redstone torch will be on, and then the light will turn on. So that represents an AND. And then we have an OR, pretty much the same thing. I made it more complex than I needed to, right? I could just use two different switches, and since these invert each other, I can literally just get rid of them. Like that's just reducing the circuit. So, but this is how you express an OR. So if you turn this on, it turns on. If you turn this on, it turns on. It's basically just these torches cancel each other out, so it's kind of redundant is my point, but that's how you're supposed to express it, I guess. And then we have NAND, which is the same thing as AND, except there's no inverter at the end. So if both of them are on, then let's think. If both of them are on, it's off. If one is off, then it's on. Both are on, off, then it's on. It's literally just AND inverted. Okay. And then you can create some other stuff, like a half an adder. Now, I didn't validate this, but it's essentially just a bunch of logical gates together to create a combinational circuit. And apparently this is something called a half adder, and I don't know what it is, but if you have two of them, you can create a full adder. But what I think this is supposed to be is if these are like bits, like off is 0, on is 1, if you were to add them, you could, I think this is supposed to tell you the first bit. When you add them, it could be like 0 or 1, and then this is supposed to be the carry bit. So what I think is going on here. So if both of them are on or 1 and you add them, obviously there'd be a carry bit of 1 and the original bit is 0. So that's what I think it is, but I could be wrong. But now, what I'm going to show you is some other things you can do. You can represent other combinational circuits, just any combinational circuit. And I will now, let me just open my book, because I've been using a book to learn about this. And so something interesting that you can do, an interesting equivalence, is between logical or combinational circuits and propositional logic, propositional logical expressions. There's an equivalence. So in this image, they say translate 1 times 0. So that times is your logical AND gate, and then plus is your logical OR. And this is just a different way of expressing the same propositional logic expression. You just have to convert 1 to true, 0 to false, and then everything else gets converted. So logical AND would be obviously same thing, and same thing for the ORs. And I guess they're supposed to be like a I don't know what it's called, but a bar above the 0 plus 1, and that represents a negation in propositional logic. So yeah, that's really nice, because that means in Minecraft we can represent combinational circuits using a circuit expression. What is it called exactly? Boolean function, I guess. Yeah, so these are just Boolean equations, or what could it be called? Anyways, it really doesn't matter. I'm just going to call them circuit expressions, because they are representative of a circuit. So this is a circuit expression, meaning x plus y. And I actually did this wrong, because there's 3 levers, meaning 3 variables, but there's only 2 variables here. So I should have just used the same signal. So I have to rework this. But this is a circuit expression, meaning x plus y is a logical OR gate, and we can see that here. This is the OR, just like from before over there. And so because one of them is on, the entire signal is on. And then we're multiplying that, meaning it's a logical AND to the negation of x, which apparently is this, but it should be that. It should be the first signal. And we negate it, and then we pass it in to a... wait, I don't know why I negated it again. I don't think I should have done that, but anyway. Yeah, we're just passing it in. We already negated it. Yeah. So we're good. Let's just make sure the signal's strong here. Yeah. Okay. Now, we're gonna do the same thing here. We actually do have 3 variables, so it works out. But here is a little more complex expression. We have 3 variables, and I did actually account for the variables here. So x has 2 signals because it shows up twice, and same thing for y, same thing for z. But the nice thing about this is that you can check it once you build it. You can go online to a truth table, because again, this circuit expression is equivalent to some propositional expression, which means I can go online to a truth table, and this is the truth table for that circuit expression. In propositional logic, you have, this is an OR, these are just x, y, z, p is x, q is y, r is z, and we have and then this is a not, so it's like an inverter, and yeah, you can just check your work. So let's try that out. So right now all of them are on, so let's see. And the nice thing, the interesting thing about this is that each column of the truth table represents a portion of the redstone circuit, which is kind of nice. So let's find P or Q. P or Q would be here. So that right there is, okay, remember, this is P, this is Q, this is R. So this little disjunction right there, these 2 repeaters, whatever the value it outputs is P or Q. And obviously we see that both these repeaters are on, meaning that P or Q is true. So we'd say this is true, and it's green because it's correct. And then we look at P or Q or R, and that's just all 3 of the repeaters. So all the 3 of the repeaters are true, they're on, meaning that the OR, if all of them is true, the OR is going to evaluate to true. So obviously that's true. and we can say true, and that's correct. And then we could do not P. Not P would be false because P is true. You can see that here, so this would be false. And then not Q. I mean, it's fairly obvious just looking at the truth table what these are, but the nice thing about it is that you can actually check your work. So this is true, meaning not Q would be false. And now it's asking for not P and not Q, which we can check by going up here, because this is the second signal. And looking at just, so that, remember, this is an AND between these two signals. Both of them are false. Okay, let me think real quick. Yeah, so we're negating it, right? We're negating it here. And then we're passing it into an AND. This is the AND, but it's 3 wide, but we can just focus on these two signals in the AND. And both the signals are on, and if they're feeding into this, let's think. So if both signals are on, oh, I see. So since both signals are on, we're inverting it here, meaning technically both signals are off in the AND, and that means this will pass in to the AND, creating a false signal. So you can think of it as like, if these signals were on, these two signals would be off, meaning this redstone torch would be on, which represents the actual AND. So since it's off, we know that the AND is false. That's true. And now let's look at not or. Sorry, not R. So this is R. We see its signal. If we come up here, we have an inverter here. And we see that it's off, so we say false. And now it's asking for the AND of every negation, which we have representing this whole section. And since they're all on, because remember in an AND, you invert both signals, or how many ever signals, n signals, before you invert them again. And so, because they're all on and the redstone torch representing the value is off, this is false. So let's see, one last one. And here we can just check this directly, because we feed in both of the signals into another AND, right? And we can just check the redstone torch, or sorry, the redstone lamp. It's off, so that means without even thinking, just looking at the circuit, this is false. And there we go, we've done one row. And for each row, we can just change the state of each lever and check our work again. And I think it's a really cool way to use redstone in Minecraft, is to verify it with a truth table. I think that's pretty neat. So yeah, it's just what I wanted to show you. So yeah, if you like it, make sure to leave a like, and let me know if you have any other interesting things to say about it. And yeah, that's it. See ya.